All right, what did we talk about last time? We talked about aldol condensation. We talked about self-condensation, where you take an aldehyde and it condenses with itself. We also talked about crossed-aldol. And you got to be really careful when you do crossed-aldol, you get multiple products. So we talked about ways to direct a crossed-aldol so that you get one product as your major product. And now we're going to talk about synthesis with aldol. So if I give you a compound or you recognize a structural feature, how do you take that apart to see how you would make it using an aldol condensation? So we're going to do a little bit of a retrosynthesis. But first of all, I want to make sure that you have on your radar the two structural features which would suggest an aldol condensation in order to synthesize those. And that would be, the two things I'm talking about are beta-hydroxycarbonyl or alpha-beta unsaturated carbonyl. If you see that structural feature, you should say to yourself, I can make that using an aldol condensation. And what we're going to do is we're going to take it apart, show the starting reagents that would be used to make that by an aldol, and then decide if it's going to work like we want, or if we have to use one of the special techniques that we use for crossed-aldol to give us exclusively one product. All right, so that's something you're going to be asked to do on midterm 2. So key structural feature. Here, remember, this is alpha, this is beta. This is alpha, this is beta. This is a beta-hydroxy carbonyl. And this is an alpha-beta unsaturated carbonyl. All right, so what we want to do is we want to have a systematic way to take these apart to see what our two reagents would be to make this. So what we're going to do is we're going to we're going to mark alpha beta. We're going to break the alpha beta bond. We're going to put a carbonyl in the beta position. And the negative charge in the alpha position. So these would be the steps. We'll call this 1, we'll call this 2, and we'll call this 3. So we've already marked alpha beta. What we're going to do is we're going to break the alpha beta bond. So I'm just going to put a line here to cut that bond and break that bond right there. We're going to put a carbonyl in the beta position. All right, so that means this would be a carbonyl. This would be a carbonyl. And then negative charge in the alpha position. So we're going to put a negative charge here and a negative charge here. And when you do that, what you end up is with these two starting materials. Notice the same starting materials here, because remember, we can sometimes get a beta-hydroxy, or sometimes we can go all the way to alpha-beta unsaturated. And so here's our negative charge here in the alpha position. All right, so if you follow those steps, that'll allow you to take it apart to see what you would, how you would make it. So now we're going to do an example here. Determine whether the following alpha-beta unsaturated ketone can be prepared by an aldol condensation. Is this feasible? Will you get only one product? So there will be a problem on the test like this. And usually the way I say it is show how you would make the following compound by an aldol condensation, and then provide the conditions for this reaction. So you would have to, if it needs directed, if you need to make an enamine first, you would do that. Okay? So I'm going to ask for both of those things. So let's follow the steps here. Break the alpha-beta bond. So here's alpha, here's beta. Put a carbonyl in the beta position, and negative charge in the alpha position. So this can be made from, and notice this is this would be made by an intramolecular aldol. And let's certainly count carbons to make sure we didn't make a mistake. We have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. All right, and so that's what we would do is self-condensation, and in the beta position here we have a negative charge. And so of course this would come from the corresponding diketone. And especially in the reactions in this chapter, you want to always make sure that you're counting carbons. Okay, so because it's easy to add or lose one. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And you want to check yourself when you do that. So here, both ketones in the same molecule. So that's how we take it apart. Now we have to see if we take that compound and we condense it using an aldol condensation, are we actually going to get that product? Remember from 51B that 5 and 6 member rings form very easily intramolecularly. Okay, so we're looking for a 5 or a 6 member ring. Let's look at all the possible enolates and see if this is going to work, because we have more than one possible enolate here. So let's draw this. So when we're forming so let's look at all the possible enolates over here and see what's going to happen. So we have, since it's symmetrical, we only have to really look at one side. We can look at this ketone or we can look at this ketone. Let's look at this ketone. If we form the enolate here, so that this carbon will be negatively charged and it cyclizes on that carbonyl, how many atoms do we have in the ring? So we count 1, 2, 3, 4, 5, 6. Would make a 6-membered ring. That's going to be favorable, 5 or 6. But you know, of course, we could also form the enolate right here, because under these conditions, this would be sodium hydroxide conditions for aldol condensation. We could form the enolate on either side. What if we form the enolate here and it's cyclized? That would be how many membered ring? 1, 2, 3, 4-membered ring. That's not going to happen. So we will get mostly one product here just by doing an aldol condensation here. So let's label those two positions. If enolate forms here, and adds to the ketone, we'll get a 6-membered ring, which is the one we want. If it forms on the other side, if the enolate forms here, we'll get a 4-membered ring. Which is certainly not favored. All right, so that's actually going to be an aldol that's going to work very, very well for us. Okay, let's look at another example here where we're asked to predict the major product. That's on the next page. All right, so we've got 3 possible enolates. Let's go through this example and see what we would get. We can form the enolate here. Let's call that A. We can form the enolate here. Let's call that B. Or we could form the enolate here. Let's call that C. And what we're going to do is we're going to look at the enolate forming on each of those, see what ring it could cyclize to, and then we're going to find out what the major product is going to be for this reaction. Okay, so let's do A first. And I'm not going to draw the arrows for that. I'm going to just already form the enolate and see where it's going to go. And I'm going to leave the electrons on carbon because I think that's a little bit easier in this chapter anyway. All right, so if that cyclizes on this ketone after several steps, and this you'll want to go home and prove to yourself by going through the steps of the mechanism. All right, so that's if we use that one. Let's do B now. Okay, so that's if the enolate forms at the B position and it attacks the carbonyl. Again, you want to prove all of these products that I've drawn to yourself. Of course, and I'm just drawing the beta hydroxy. We could heat that up and we could get to go all the way to the alpha beta unsaturated. But right now we're just seeing what kind of, what's going to be favored here. So that would be the product if we form the enolate at position B. All right, and so that's actually going to be a ring that's larger than 6, which is not going to be favored. So an 8-membered ring, I know you guys hate drawing 8-membered rings. So it's just like a stop sign, no big deal. So now let's analyze each of these products. All right, so let's go back to the first one and see and analyze what we have. So we're forming the enolate in the position A, we're attacking a ketone. So ketone is attacked. Here we're forming the enolate in the B position and we're attacking an aldehyde. Aldehyde is attacked. What's more favorable, a ketone being attacked or an aldehyde being attacked? Aldehyde being attacked. Okay, so ketone attack plus a 6-membered ring. This is aldehyde attacked plus a 6-membered ring. And so aldehyde's better. So this one's going to be better. So ketone attacked is not going to be favored at equilibrium, especially when we have an aldehyde that can be attacked. Not favored at equilibrium. And then certainly, so down here, what do we have? We have aldehyde attacked. That's favored, but we're forming an 8-membered ring, and that's not favored. So also not favored. So what is the major product we're going to get? B. B's the major product. Yep. And if we add heat, then we would form the condensation product. And that's going to drive it all the way to this product right here. That will be the major. All right, questions on that example? Anybody? A lot of thought process going into that. That's not going to be something where you can just memorize the answer. And that's really the key with the problems in this particular chapter, not going to be able to just memorize the answers. Okay, so there is going to be some thought process, which we've been building up for, well, this is our 7th week, right? We've been building up all of that knowledge. And now it all comes into play in this chapter. All right, I hear some little bit of like, oh no. Okay, this is a classic midterm example. You will see one like this, only of course I will change the structure. So I want you to know what you're going to need to be able to do. Show the 2 organic starting materials that would be used to synthesize the following ketone by a crossed-aldol. So we're going to just take it apart, see what we get. Next, we have to actually, this is where we're kind of asking ourselves, how are we going to actually make this happen? Do we just throw the 2 things together with sodium hydroxide, like a typical aldol, or do we have to do some sort of directed aldol? Do we have to make an enamine? That's what we want to do. All right, so the very first thing we're going to do is we're going to take this apart using the steps we talked about on the previous page. Start counting from the carbonyl. Alpha, beta, we're going to break the alpha-beta bond. We're going to put a carbonyl in the beta position. And we're going to put the negative charge in the alpha position. And then we're going to draw those 2 starting materials. So it would be that plus this. So by putting the negative charge in the alpha position, we can see what's the enolate that we really need to make. Okay, now we're going to analyze these 2 and see if this is actually going to work for us. In order not to get multiple products, we need just 1 enolizable hydrogen. Do we have just 1 enolizable hydrogen? No. On this one, there's really only 1 because it's symmetrical, so either side would give us the same one. But we have an enolizable hydrogen on the other compound too. So here's an enolizable hydrogen. And then we have only 1 enolate for this ketone. So if we just do the classic Aldol conditions, which is throw these guys together with sodium hydroxide, we are not going to get just 1 major product. Once we form the enolate, what is the most likely carbonyl that's going to be attacked? What's more electrophilic? Aldehyde's more electrophilic. So, but since we have 2 different enolates, we're going to get 2 different products. We don't want to get 2 different products. We want to just get 1 product. So when you provide your conditions for the crossed-aldol, you want to provide conditions that are going to give you 1 major product. So what we're going to do here is do a directed aldol. So rather than throwing both of these things together with sodium hydroxide, we're going to form the enolate completely with the compound that we want to form the enolate from. Then we're going to add the other compound. So you're going to have to make that decision. Do I need a directed aldol, or do I need to just use this classic aldol where you just throw everything together? So LDA-THF minus 78 degrees. That's going to give us the enolate. In order to be able to do this, you're going to need some practice. So you definitely want to do as much practice as you can here. We have, of course, gotten to the point where you can't memorize the answers at this point. You're going to have to think your way through them. Then we add the aldehyde. We need to protonate that oxygen. What do we want to protonate that with? What do you think? Do we want to use water or acid? What happens if we use acid? It's going to go to the alpha beta unsaturated, right? So the acid catalyzed aldol, if we add acid, this is going to want to, that hydroxyl is going to want to come off. We're going to want to go to the alpha beta unsaturated. So we definitely want to use water, not acid. Okay? H2O, not H3O plus, because if we use H3O plus, you're going to get the alpha beta unsaturated. So if you are forming an alpha beta unsaturated compound, then you definitely want to use acid in your second step. So once again, you're going to have to think for these problems. Questions on aldol? Anybody? So we'll have some examples next week in discussion that we'll work through, so you have a chance to go through that thought process. No questions? We're going to start Claisen now. So a bunch of name reactions in this chapter. So Claisen condensation, enolate plus an ester. And the classic Claisen is when you take two esters and they condense with each other. So notice the two here. It's just going to be a self-condensation. Let's draw the product and then let's go through the mechanism. Claisen condensation has appeared on many of my midterm 2s for 51C. So I'm just throwing that out there. This is a two-step process. Product is a 1,3-dicarbonyl. Also, be more specific, a beta-keto ester. And we saw beta-keto esters in chapter 23, didn't we? We used those, we alkylated, and then we hydrolyzed and decarboxylated, okay? So that's one of the things that this is one way to do that. So notice it's completely different than an aldehyde. Aldehyde condensation, you get a beta-hydroxy ketone or aldehyde or alpha beta unsaturated. Here you get a 1,3-dicarbonyl. So 1,3-dicarbonyl needs to be on your radar. So if you see it, you can say to yourself, I might be able to make that by a Claisen condensation. Okay, so that's the structural feature you want to look for. All right, let's look at the mechanism here. Now, notice the Claisen it's only base catalyzed. We're not going to have an acid catalyzed Claisen. So that makes life a little easier for you. We're going to make the enolate, and again, you have a choice. You can move the electrons onto oxygen, or you can keep them on carbon. I'm going to try to go back and forth here. So this time I'm going to move them onto oxygen. And notice we have reversible arrows here. This is thermodynamic conditions. Let's try that again. Okay, so we make the enolate out of one of the esters, and it's going to add to one of the other esters that has not been deprotonated yet. Okay, so remember the key thing here is once we deprotonate that alpha position, now we turn this into a nucleophile. So that's a nucleophile. And so now it's going to attack an electrophile here. All right, so electrons on oxygen come down. And we attack the carbonyl, kick electrons up onto oxygen. We're going to get a tetrahedral intermediate. So take a look at that tetrahedral intermediate and tell me what's going to happen. Do we have a leaving group? So tetrahedral intermediate has leaving group. So if you've internalized everything we've learned so far this quarter, this is going to be easy for you to make these decisions. We're going to have the electrons come down and kick off ethoxide. All right, we didn't have a leaving group in the aldol, did we? So that's why we got a different product. So compare with the tetrahedral intermediate that we had in the aldol. And because we're attacking an aldehyde, we don't have a leaving group, right? Because that's a type 1 carbonyl. So compare with tetrahedral intermediate formed in the aldol reaction. Now we have a leaving group. So this goes all the way back to chapter 20. All right, so that leaving group's going to leave. Then what happens? Okay, so what do we know about, we just kicked off a ethoxide ion. What do we know about what's going to happen next? Can't we just isolate that? Why do we have to add acid? We already formed that. Why can't we just isolate that? You can't not, what's going to happen is, and we went through the thermodynamics of this. I mean, we went through the acid base. Whatever, this proton's going to be removed from that ethoxide that you just kicked off. And that's actually what drives the equilibrium in this reaction. So in the aldol, we drive the equilibrium by losing water. This actually drives the equilibrium for this reaction. So number one, you can't stop this from happening, because you're forming this in the presence of base. You're forming this in presence of base that is strong enough to completely eliminate, to completely remove that alpha hydrogen. And this drives the equilibrium because you're creating a very stable intermediate. This is highly resonance stabilized. So we can push electrons onto this oxygen. So now I'm going to draw resonance structures here. We could also go to the other side. We can go all the way over here. We can move electrons all the way up onto this oxygen. So super important that you draw this. Formation of this drives the equilibrium. If you cannot form this deprotonated active methylene compound, if you cannot deprotonate that position, maybe there's alkyl groups there, you can't do a Claisen. You have to be able to form this, or you can't do a Claisen. And so that's what it's talking about underneath here. Reaction of the equilibrium process and thus reversal. Because of this, the Claisen condensation does not give a good yield of the beta ketoester unless the product is converted into an enolate in the basic reaction mixture. So this is key right here. The intermediate simply undergoes the reverse reaction and decomposes to give the starting enolate and ester. If there are no alpha hydrogens to deprotonate, then the reaction won't go. And so that's right here. So let's say we try to do a Claisen with this compound here. This one only has one alpha hydrogen. You will form this, but I'm putting it in brackets because it's not stable. Notice there are no alpha hydrogens to deprotonate. Therefore, you can only isolate very small amounts or none at all. So when I say very small amounts, I mean 1%, 2% maybe. And so therefore, you can't synthesize this compound by Claisen condensation. Can't synthesize this compound. And I always want to put 2 S's on that Claisen, so we'll fix that. Okay, it looks a little bit, when I do that, it looks a little bit like Claisen, you know, like Claisen pickles. Always want to put 2 S's there for some reason. Okay, so can't synthesize that compound. How could you synthesize that compound but not using a Claisen? What could you do? How would you do that? How about making this without the methyls here and alkylating twice, like we did at the end of chapter 23, right? So that's the way you could do it. You make this without the methyls, and you can make this without the methyls by a Claisen, and then you can alkylate twice. And that's how you would make it. You just can't go directly from this to that. Not going to happen. All right, questions on that? That's a kind of a key point here. Questions on Claisen condensation mechanism? All right, so let's look at crossed Claisen. All right, and so like the aldol, we're going to have to choose our reagents very carefully if we want to get just one product when we are doing a crossed Claisen. So the mechanism I showed you, that wasn't a crossed Claisen. But if we want to do a crossed Claisen, we've got to choose reagents really carefully. And so that means that we have to know a little bit about reactivity, which means that all the work we've been doing for the last 6 weeks, this is our 7th week, all pays off now. If you crammed for midterm 1, all of that's gone, and you're going to have to go back and remind yourself. So, you know, when I put all those reactions, the structure reactivity problems at the beginning of the exam, rank the electrophilicity of these, all of that's necessary to be able to do chapter 24. So those of you who have kept up to speed, it's all going to pay off right now. Here's your reward. Okay, so a couple ways to do this. Choose reagents so that one of the participants is especially reactive or has no alpha hydrogens, so only one enolate can form. Doesn't that sound familiar? That's what we were doing with the aldol on Friday. Okay, so let's look at the combination here. Only one enolate can form, so we're going to form the enolate here. The other compound has no enolizable hydrogens. So no enolizable hydrogens. So already we're off to a good start. Now, once we form the enolate on the first compound, which carbonyl is that more likely to attack? Aldehyde, right? Aldehydes are more electrophilic. That's a half aldehyde. The other one's a half ketone. The esters part's the same. And so this is going to be this compound here. Once we form the enolate on the other compound, this one is especially reactive. Because it's a half aldehyde. So that means that this is going to be a good reaction. You're going to mix these two esters together. You're going to get predominantly one product. Because we're only forming one enolate, and that enolate is selectively going to attack the most electrophilic carbonyl, which is on the other one. All right, so that means this is your product, and you definitely want to go back and prove this to yourself. So sort of the first thing with these condensation is being able to draw the correct product. So that's what you're going to get. So prove to yourself. So cover up the answer and see if you can get it. See if you get the same answer. All right, so that's one way. We might not always have that luxury, though. So let's see. Maybe we have some other ones that we're not going to be able to do that with. So second way, aldehydes or ketones can also be condensed with esters. If addition to an ester is desired, the ester should be especially reactive. All right, so let's analyze the two of these. This is going to be a condensation reaction. And it looks like we only have one enolizable hydrogen right here. So that means we're going to form the enolate on the ester. The aldehyde has no enolizable hydrogens. All right, so once we form the enolate from the ester, what is it more likely to attack? Aldehydes, right? Aldehydes are more electrophilic than esters. So that was not wasted. All that time you spent learning the relative reactivity. Again, it's all paying off here. So no enolizable hydrogens, and it's also the most electrophilic. So if you're going to form the enolate exclusively from one and it's going to attack exclusively the other, then you've got a good Claisen. So let's actually go through. I'm not going to do the whole mechanism, but we're just going to show how you draw the product. So I'm going to show the enolate already formed. And I'm going to show it attacking. Now, this is really going to be kind of a mixed. It's not really pure Claisen. In a pure Claisen, you attack an ester, and we're attacking an aldehyde. So this is not a pure Claisen, but you can still do condensations when you mix the two of these. You just have to know what you're doing. So does there's our tetrahedral intermediate have a leaving group? The only leaving group it has is to reverse itself, and it can reverse itself. But as far as leaving group, productive leaving groups that are not going back to starting material, we don't have. And so this is going to be more aldol-like, because we're attacking a type 1 carbonyl. So no leaving group. So we're not going to get too caught up in is this a pure Claisen, is this not a pure Claisen, is it an aldol? We're too worried about that. And so what's going to happen is we're going to protonate like we did with an aldol. Oops. So we're not going to get a carbonyl like I just started to draw here. We're going to get this. And it turns out that we can't really stop at this position here, at this one. It's going to keep going all the way and lose water, even without heat. I'm going to draw out the phenyl ring so you can see why. Why does that lose water without heat? We saw one like that already. The double bond that you form when you eliminate water is conjugated with the benzene ring. So we have this highly conjugated system. We have the carbonyl, double bond, single bond, double bond, single bond, double bond, single bond, all the way around here. Okay, so you can't isolate the beta hydroxy. So you have to know that that goes all the way to the alpha beta unsaturated carbonyl. Questions on that one? Yes? I did. I'm not showing the whole mechanism, but yeah, you're in. In this case, we would protonate with ethanol rather than water. Okay. Yeah, we definitely, we definitely want to use, if there is an ester involved, you want to choose your base to match the ester. What if I use sodium hydroxide here and water instead? What would happen? Because this is actually more like an aldol rather than a Claisen. What would happen if I added sodium hydroxide to that? What's going to happen? What chapter 22 reaction is going to happen? Saponification of the ester. You won't get condensation. You're going to get hydrolysis of the ester to a carboxylate, and then that's going to be the end of it. So in this case, we're going to protonate with ethanol rather than water. All right, you want me to show that? Yeah, let's do that. Let's show that. Even though this isn't a complete mechanism, we're going to protonate here with ethanol rather than water. There was another question over that side? No? Yes? You can, yeah, if you didn't have a benzene ring, if this was, say, a methyl, you could stop here. But remember, you can't get all of this. Remember, when you attack an aldehyde, it was like 55% of this. So really, to get it to all go to one thing, you want to drive all the way to this product. Okay? All right, so so the other thing we want to do let's get some more examples. So you will see something like this on the midterm, and when you see some sort of base like this, sodium methoxide, ethanol, or sodium hydroxide, water, and heat, that you're going to know it's a condensation reaction. Okay, so let's see what's going to happen here. Do we have any enolizable hydrogens here? No, we have an enolizable hydrogen here. Fortunately, this is symmetrical, so there's only one enolate we can form from that compound. So let's label that one. Either side, I'm going to go here. Enolate will form here. And it turns out if you're comparing reactivity, this is a formic ester, and the formic ester is actually more electrophilic. So this has no enolizable hydrogens. And it's especially reactive because it's a half aldehyde. So it turns out that the ketone is more sterically hindered, and so you're going to favor forming attacking the formic ester. So ketone more hindered than formic ester. All right, so let's go through the thought process here rather than just drawing the product. Let's go through the thought process. This is not the complete mechanism. So there's our enolate. You can go on either side here. Both sides are identical. And then we're going to attack the formic ester. So because we're attacking a type 2 carbonyl, we're going to have a leaving group. So let's push electrons up onto oxygen here. Let's take a look at our tetrahedral intermediate. And as you can see, here's our tetrahedral intermediate. It has a leaving group. So this is going to be more Claisen-like. So that means the electrons on oxygen are going to come down, and rather than a beta hydroxy, we're going to get actually a carbonyl in the beta position. And now that ethoxide that we just kicked off is going to come and remove this active methylene proton, and that drives the equilibrium. Questions on that example? Anybody? All right, so there, the previous one was an aldol-like. This one was a Claisen-like. We're not going to get too caught up in the names. We're going to be able to, but we are going to be able to figure out what the product is by using all the things that we've learned about with carbonyl-chemistry. All right, so third strategy here is going to be reacting enolate with ethyl chloroformate or diethyl carbonate. These guys are especially reactive. Both of these. Especially reactive, they're especially electrophilic, and they have no alpha hydrogens. Okay, so we can take whatever we want. We can take an ester, we can take a ketone, and we can condense here. So we're going to form the enolate. Form the enolate here. I'll just do it on this side here. Enolate forms here. And the ethyl chloroformate, no enolizable hydrogen. And it's especially reactive since it's a half acid chloride. Okay, so that means we're going to predominantly form one product. Let's go through the thought process that we would use for that. So again, this wouldn't be a mechanism. This is just our thought process if we have predicting the products. So then we have the acid chloride. Very electrophilic. Push electrons up onto oxygen. And then we take a look. All right, so what happens now? Does our tetrahedral intermediate have a leaving group? It has two leaving groups. Which leaving group is going to leave? Chloride's the best leaving group. That's the best leaving group, right? So electrons are going to come down and kick off the best leaving group. Can we stop there? No, we're going to have to deprotonate. Long arrow to the left, short arrow to the right. We're going to deprotonate. That's what drives the equilibrium. And so in a second step, we add acid. All right, questions on that one, anybody? I'm going to have you come up because it's 12:50, so you come on up. We'll stop right there. We'll continue this on Wednesday.